Chapter 4. So we went through Chapter 3 fairly quickly, 2 lessons. We're going to go through Chapter 4 kind of quickly. I'll slow down a little bit more on this one. This chapter does require a little more arithmetic. That being said, most of this is something you've probably seen before. Whether you remember it or not is different, or whether you remember how to do it or not is different. But there's a very good chance that you've worked with this material before. So we're looking at slope and linear functions. So we've talked about functions a little bit, exactly one range value for any given domain value. Now what we're looking at is a specific type of function called a linear function. And we're going to go into that a little bit. So slope is a really important topic for lots of mathematics. It's a really important topic for algebra. It's also a really important topic for geometry. And it's kind of the beginnings of calculus. And so slope just transcends a whole bunch of different areas of mathematics. So it's an important idea. Slope is the rate of change. Things change. We want to know how quickly or how slowly are they changing, and how quickly and how slowly are they changing at different intervals. Like, how much is changing could change as things go on, as time goes on. So slope is all about change. It's how fast things are changing, the rate of change. And we compare that, or we can find the rate of change by comparing the vertical change, which we usually talk about with the y-axis on a graph, and the horizontal change, which we typically denote with the x-axis on a graph. So it's that ratio of the vertical change compared to the horizontal change. So in general, broad sweeping ideas here, a negative slope is when the vertical change is going down as the horizontal change moves to the right. And we typically go from left to right, kind of like how we read from left to right. So if you're reading from left to right and the line is going at a downward angle, we call that a negative slope. If you are reading from left to right, it's just flat. You have a zero slope. That'd be like a table or a desk you'd hope would have no slope. It would just be nice and flat. And a positive slope, if you read from left to right, is going up from left to right. So there's a positive vertical change and a positive horizontal change. So that's general, again, looking at the picture, is it going to be a negative, a positive, or a zero slope? Calculating that slope, what number do we assign to how steep something is? Because really steep, kind of steep, sort of steep aren't very precise mathematical terms. So we use this concept of rise and run. And that's a very, again, not very mathematical way of looking at it, but you're going to hear that a lot. And it's a nice way for us to describe the vertical change and the horizontal change. So when we talk about rise over run, the slope, we usually use the letter m to represent slope. The slope m is the rise over the run. And that's if you're looking at a picture, if you're looking at a graph, the vertical change we call the rise. You got to rise up. And then the horizontal change is the run. That's what it's referred to as. So the vertical change between any 2 points on a graph, so you're given any 2 points, there's an infinite number of points on this graph. If you pick 2 of them randomly, the vertical change between them compared to the horizontal change between them will be the same as any other 2 points on the graph. So I pick another point down here, let's say right there, and I compare it with these 2. I would get the same vertical change and the same horizontal change as with these other 2 points here. And this is the algebraic form. So basically, if we're given 2 points, we've got an x and a y, an x and a y. We're going to find the difference between the y's, because that's really what the vertical change is here. It's how far apart are the y values, the difference between them. And the horizontal change is the difference between the x values. How far apart are these 2 numbers? Here's an example. So I've got find the slope between any given points. We're going to look at the geometric and the algebraic at the same time and see how they work together. So I'm going to plot those 2 points on a graph. There we go. I put those points on the graph. And if I look at the formula, the algebraic, the formula, this is what the formula says. Now, before I look at that or plug numbers into this formula, remember the rise was the change in the vertical, and the x was the change in the horizontal. So back over here, the vertical change between those 2 points. Again, this isn't counting at a diagonal. You don't count at a diagonal because that's not going to give us a nice number sometimes. So we want to count straight up and down the vertical change, or count straight across the horizontal change. So imagine that there's a right triangle in between those 2 points. The vertical change, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you're given a picture, it's fairly easy to just count up and down, 10, and across, 1, 2, 3, 4, 5. There we go. So the slope should be a rise of 10, a run of 5. 10 over 5 should be the ratio of the rise to the run, the vertical change to the horizontal change. The slope should be 10 over 5, which is 2. If we look at the formula, because sometimes you're not given a picture, if you're just given 2 points, to use this formula, it says y2 and y1. That doesn't mean y squared. You'll notice it's a sub 2, it's below the y. It just means that there's 2 different y's. There's a y and there's another y. It also doesn't matter which of these points is y2 and which one is y1. So it really doesn't matter, as long as you're consistent. So if you want this point here, -3, -4, if you want that to be y2 and x2, that's fine. And 2, 6 would be x1 and y1. That's fine too. It'll work. There's nothing to stop you from doing that. It'll work every single time. Be consistent though. If you always use the first number as y2 and x2, great. Use that first point as x2 and y2. And if you always use the second number as the first point, 2, 6, going here, 2, 6, great. Do it that way, but be consistent. As long as you're consistent, it'll be fine. So I'm going to choose the second one here. I'm going to say 2, 6 is my y2 and x2. And I'm going to say that -3, -4 is x1 and y1. So I plug those in. I'm going to find the difference. 6 minus -4 is 10. 2 minus -3 is 5. I'm going to get the same result as I have here, 10 and 5. 10 divided by 5 then is 2. So we would say the slope of this line is 2. Some more unique situations. Most of the time, I'm going to go back here a little bit, most of the time your graph line is either going to be a negative or a positive slope. Most of the time they're at an angle of some sort. However, they could be they could have a 0 slope, or what we call an undefined slope. I'm going to show what those two look like. So given these 2 points, 3, 7 and 8, 7, if we plug in that information, again, I'm going to say the second one is y2, x2, and the first one is x2, x1, y1. So I plug those in, 7 minus 7, 8 minus 3. We find the difference between the y's, the difference between the x's. I'm going to get 0 divided by 5. 0 divided by 5, if you have nothing and you divide it between 5 people, everybody gets nothing. So 0 divided by 5 is 0. That's the slope. The slope is 0. And that's fine. We can have a slope of 0, be like a desk or a table. So our graph would look something like this. It would be a nice flat line. And that would be our graph for this. So 0 slope, that's what the graph looks like. So when you get a 0 slope from numbers, that's kind of the picture that you should have in your mind. It's a nice flat line. Finding the slope of these 2 points. So we've got 1, 5 and 1, 12. And if you want to pause it and do it on your own quick, once you're comfortable with it, that's great. So if I plug those numbers in, again, I'm going to use 12, 1 as my second point and 1, 5 as my first point. 12 minus 5 and 1 minus 1 is 7 divided by 0. Now, 7 divided by 0 is not 0. Check it in your calculator. It's not infinity. So if you have a calculator that says 7 divided by 0 is infinity, throw the calculator away. Bad calculator. It's not infinity. It's not 0. And it should give you some kind of an error, is what you should end up having. This is undefined. You can't have $7 and put it into 0 piles. It's got to go somewhere. Even if it's under your bed, it's in a pile under your bed. You can't divide something into 0 sections. You have to put it in at least one section. And so it's just not a defined term. You can't divide by 0. World implodes, bad things happen. This is what the graph looks like. So a graph for an undefined slope is a vertical line, straight up and down line. Most of the time, your line will not be straight across and it won't be straight up and down. A graph line will be at some angle. However, it is possible to have 0 slope, and it's certainly possible to have a line that goes straight up and down, to have an undefined slope. But that's how we talk about 0 and undefined slopes. some modeling of this. So rate of change isn't always just graphs. Rate of change could be just how much are things changing. So the question in this problem asks about a car that's being driven on a tank of gas, and they want to know between which measurements was the gas mileage the least. So we've got 0 to 60 miles driven, 60 to 150 miles driven, 150 to 170 miles driven, and they were able to somehow measure how much gas was used at the first section of driving, middle, and last section of driving. So if we want to find out during which two sections of the time driven, of the miles driven, was the gas mileage the least. Gas mileage, remember, is miles per gallon, is how we measure gas mileage. So miles per gallon. We want to compare the miles and the gallons, but we're not just doing 0 divided by 0 or 60 divided by 2. We want to talk about the change. I want to talk about the rate of change. So between 0 and 60, 60 miles were driven. And between 0 and 2, 2 gallons were used. So we would say 60 minus 0, 2 minus 0, we get a gas mileage of 30. Now we have to check between 60 and 150, and 2 and 5. So we would subtract, again, y2 minus y1, x2 minus x1. We'd have, again, 30 miles per gallon. 150 minus 60, you can do the subtraction. Then we have to check between 150 and 170. So we're looking at how things are changing and what's the rate. At what rate are they changing? So we would compare 150 and 170, 5 and 6. The least gas mileage is going to be between 150 miles and 170 miles for this particular car. It had an average gas mileage of 20 miles per gallon on that for that section. So that's where you see, or where you could see, rate of change, not just on a graph, not just in algebra, but anytime you're comparing how quickly things are changing. X-intercept and Y-intercept. So again, going back to kind of graphing and more static algebra stuff, X-intercept and Y-intercept are generally nice things to know if we can. And that'll come up more throughout this chapter and next chapter. If we look at this graph, looking at a graph, it's actually really fairly easy to find the X-intercept and the Y-intercept. The X-intercept is where the graph, here's my graph line, touches the X-axis. So the X-intercept, -1. The Y-intercept is where the graphed line touches the Y-axis. So the Y-intercept would be 2. If you're given a picture and it's at a nice even integer here, because sometimes it's hard on a graph to see fractions and decimals, then it's pretty easy to find the X and the Y-intercept. However, if you're just given an equation, so let's say the equation for this line looks like this. If I want to find the X-intercept and the Y-intercept and I'm not given a picture, you'll notice that I'm going to try and find the Y-intercept here. You'll notice the Y-intercept is always on the Y-axis, and the Y-axis is always where X is 0. So the Y-axis is where X is 0. No matter where this graphed line crosses the Y-axis, anywhere along this Y-axis, X is always going to be 0. So I can use that. I'm going to plug 0 in for X. So if I want to find the Y-intercept, I'm going to keep Y, and I'm going to replace X with 0. -2 times 0 is 0. Y equals 2. So the Y-intercept would be 2. 0, 2. X is 0, Y is 2. And that's what we see here. 0, 2. That's that point. I can do the same thing for the X-intercept. So if the problem says, here's an equation, find the X and Y-intercept. I have to find the Y-intercept. We leave Y alone. We replace X with 0 because it's right on the Y-axis. We want to find the X-intercept. We can do the same thing. We want to find where the graph crosses the X-axis, which will always be when Y is 0. So the vertical axis, Y is always 0, and X is going to have some value. So I'm going to replace Y with 0. I'm going to find that X-intercept then. So I can solve, simplify, -2 plus X equals 2. X is going to be -1. Sure enough, that's what we see over here. The X-intercept is at the point -1, 0. So that's how we can do it both from the graph and just using algebra. Slope-intercept form for the equation of a line. So if we're asked to write an equation, there's a couple ways you can write an equation for a line. The slope-intercept form is the best form for graphing, typically. the easiest way to graph a line is to look at it in slope-intercept form, typically. And so this is how slope-intercept form is set up. X and Y represent every point on the line, because there's an infinite number of points on the line. So X and Y represent all the points on the line. B, here, plus B, is a very special point. So it's one particular point on the line. It's the y-intercept, which we just talked about. And M is the slope, which we talked about at the beginning of the lesson. If we look at this equation here, this is not in slope-intercept form. One type of question you might be asked to do is to get an equation into y-intercept form. So we can do that by getting y by itself. Y-intercept form, or excuse me, slope-intercept form has y all by itself. We're going to isolate y. So to isolate y, I can add 2x to both sides of this equation. I'd get y equals 2x plus 2. Now, if you did plus 2 and you got 2 plus 2x, that's correct. However, it's easier to put it in this form simply because that's kind of the standard, is to put the x first and then the plus b. If we look at this equation, though, this equation says that 2, this plus 2 here, 2 is the y-intercept. If we go back here to this equation, or this graph, here it is. 2 is the y-intercept right there. So that meets what we found in this y-intercept, 0, 2. So that was our y-intercept of 2. The slope is 2. Right here it says the slope is some number being multiplied to x. Well, 2 is the slope. If we go back, way back to the beginning, maybe I should just exit and go back. Here we go. We found, here's that same graph. The slope was 2. Y-intercept was 2. The slope was 2. So this equation does match with all the other things that we've been doing. I'll just skip down here to here. So this equation, y equals 2x plus 2, does give us the right y-intercept. It does give us the right slope of 2. Okay, I'm going to pause it here and do a second lesson after this.